Okay, so this is lecture 21st. Okay, so this is the second lecture for our level set method discussion. So I hope that we can make it quite short because the lecture content is not that much. So in the previous lecture, we just convert our initial structure into initial level set function. So in this case we will call it as just a certain phi, capital phi, whatever. So let's just consider this previous example. If we have for example certain nanosheet, and here we have a closed surface, and if we are working with the conventional method, then usually we introduce a certain explicit mesh for describing the shape of this nanosheet. However, instead of defining so every point corresponding to the boundary, so we just introduce a certain function called as level set phi, and if this is negative, then this is interior, negative, negative, and negative happen to be, let's say, if these points have the value of function equal to 0, then we implicitly assume that okay, this is the boundary of our structure. So now once we convert our boundary description from this explicit form to this implicit form, then later by using this level set function we can proceed such kind of deposition or etching simulation. We will quickly consider this one, but in order to understand how can we describe this change of level set function, first of all we have to define something like this. So time derivative of our level set function. For example, if you wanted to calculate the change of electron density, then you had to solve the electron continuity equation, and in the case of a hole you had to solve a hole continuity equation. Quite similarly, if you wanted to know about the change of a level set function, then you have to specify the value of its time derivative. So here we have the form shown here. So time derivative of level set function is given as something. So what is something? Something here means that the gradient of phi and velocity function and its inner product. So please note that phi itself is a scalar function, and this velocity field is corresponding to a vector field. So this gradient makes another vector field, and we can define the inner product between them. So we have to understand what is this velocity field. So here velocity describes the interface motion. So let's think about this circle. So this is t equal 0, and it is now expanding. How can we expand? For example, by doing such kind of isotropic deposition. So after some time later, we have the boundary shown here. Then certainly we can define the velocity v for this point. Okay, this point is moved into here, and this point is moved into here, and this point moves into here. So what is the velocity v in this case? Then of course for this particular example we have the values really depends on its point. So it's not like this. So everywhere constant. It is not position independent quantity, but it really depends on the position variable. So by applying this one, we can expand it. If we have different direction, for example, velocity is headed into the center of this circle, then what will happen? So after some time later, we will have a shrunken circle out of this action. So we can easily have this one. But point is, we must understand this velocity v is a function of position. So position here means that in our case, our x y direction, all over our xy direction, we need certain value. So although we are interested with only interface movement, but in principle actually we must consider the velocity all over our space. Then how can we do that? For example, let's just think about this one. If we say velocity is defined on this on the red circle only, and otherwise the velocity is vanishing, then what will happen? If we have such kind of a situation, then only this red line is expanding, and in a circle this green line do not move. So actually what is the can I say in that position, so actually the atoms originally located here does not move into that part. Actually what we have is certain molecules are coming into our system, and it is attached to our pre-existing system, and the boundary is moving. So although the boundary is moving, but actually the atomic speed is just 0. So the atoms are just there. So a concept of this velocity or velocity of boundary is not directly related with the velocity of our atoms inside our system. So it is very difficult to define a good values of v function here. What is v? And how about this v outside our system? So of course, also in the case of outside of a system, our boundary does not our molecules are not moving, and actually when we have a little bit expanded version of this one, of course our phi should be reduced, and yes, so therefore assigning the proper velocity, that is a little bit difficult. So we should be careful about how can we assign this problem. However, if we restrict ourselves only nearby the interface, the things can be much easier. So also please be careful with the sign in here. So when v is aligned to this the direction of gradient of phi, then phi is reducing. So please don't be confused. For example, from the viewpoint of this point here, let's say that previously it was phi was 0.1. However, by action of its expanding, now later we had to, well, let's assume that now this circle is expanding up to this red dot. Then after that, what will be the value of our phi? In this case, of course, our phi value should be 0.0 because this point is now laid on the surface. So simply speaking, when V is given here, so this is the direction of V, and what is the direction of our gradient of phi? So previously it was 0.1 and previously it was phi equal to 0. So direction of phi is also heading this outward direction. So when we calculate this quantity, so V that gradient of phi, of course it gives us a positive number. So when this is a positive number, actually phi should be reduced, so you know that here we have a negative sign. Another way to understand this one can be interpreted in this way. So when we just combine them all, then this is related with this kind of operator. Phi equal to 0. So this right hand side term is moved to the left hand side, and we just merge them here, and here V is nothing but defined as certain quantity like so like time, sorry about that, time okay, so now it is defined as time derivative of our position. So okay, so I have to say that this just D. So oh, sorry about that, so I'm a little bit confused. So this is, so let me just say that if we have the total derivative in our R and T surface of space, then it can be represented as the partial derivative with respect to the position, and also partial derivative of T and R, and yes, it can be decomposed into these two partial derivatives due to the action of chain rule. By applying this chain rule, we can make this expression. So please have a look at this part. This is nothing but just the total derivative of our phi function, and if we are observing our phi function at interface, then what is the value? What is the value of our level set function at interface every time? So it is defined as just 0. So the time derivative, total time derivative of a scalar value 0 gives us just 0. So as shown here, this function or this equation simply states that at phi equal to 0, so its total time derivative is kept as 0. So okay, so my explanation right now is not that clear, but please try to understand the physical meaning of this equation. This equation is called as a level set equation. So this is closely related with the total time derivative of level set function. Okay, so now let's come back to this equation, and if we accept the form of this level set equation, then we have to calculate this gradient of phi. Okay, gradient of phi can be defined everywhere. It's not that difficult because already we know phi at every node in our rectangular grid. So from this one, once the velocity is given, then we can calculate it. However, if we introduce a certain approximation like phi, so level as a signed distance. So please remember that when we first define level, so the condition for the level set function was, okay, it can be a positive number and can be a negative number in inside value, and at boundary it should be 0. This is the minimum requirement for this level function. So we can define actually many different values or level set function to the same interface. Let me just give one example here. Okay, let's wait for a while because our pencil is stopped. Okay, so now think about two different possible level set functions. Here we have a unit circle. Yes, and let's try to introduce two different level set functions. One is like this, r square, of course minus 1, and another one is r minus 1. So then please try to understand which one is the signed distance and which one is not a signed distance. So following this one, if we have an origin, our phi function will be just minus 1. Okay, and it's inside this part we will have negative value, and on the boundary nodes, so of course we will have phi equal to 0, and outside of this circle, of course we will have positive value. So it satisfies the minimum requirement for the level set function. Good. And please try to check whether it is corresponding to signed distance or not. For example, from this origin, yes, it is corresponding to minus 1. Good. And how about this? The midpoint r equal to a half, then we will have the values corresponding to phi equal to minus half. Okay, this is corresponding to a signed distance. Please check same thing with this a little bit different one. In this case here we have phi equal to minus 1, yes, also phi equal to 0, yes, and for this part phi is positive, so it satisfies the condition for the level cell function. But please check this half point. So in this half point r equal to 0.5, then what will be the value of phi in this case? It becomes just minus 3/4. So in this case, of course, the distance is just a half, 0.5. So simply speaking, this one, although it satisfies the level set function condition, but at the same time, it is not a signed distance function. So since we are currently working with this level set, which is defined as a signed distance, so in this case what we can have is this gradient of phi function is corresponding to the normal vector of this direction. So let me just think about this one. Here we have a vector field, and it can on the interface node, we can decompose it into two different quantities. One quantity is a normal quantity, and this one will be just headed to the normal direction. Of course, we can define another component corresponding to the on plane component. I mean that, for example, in this case, what is normal direction? Yes, this is the normal direction, and we can define the other direction. And of course, we have some quantities, the velocity quantities corresponding to this one. But happen to be, if we take the phi as a signed distance, then we can say that in this point, gradient of phi is precisely corresponding to the just normal unit vector. So in this case, the inner product between this on plane component and this normal unit vector gives just 0. And how about this? The n dot n gives us also just unity. So that's the reason why here we have quite a simple answer, like taking only a normal component. So please note that this kind of simplification is possible only when we consider phi as a signed distance, and also this is strictly valid only for our position nearby this interface point. But we will just use this simple one. It means that there is no longer any kind of derivation. So velocity, this is a scalar function. So if we can define the values of normal velocity at each boundary point, then we can just increase it in somewhere. And for other parts, of course, non-boundary points, maybe determining this normal velocity would be quite difficult. But in this simple example, I will just use the constant value. So let's think about the meaning of this constant value. So let's say that this is our current boundary, and we have V normal equal to, for example, a certain constant C. Then what does it mean? It means that for this boundary value, so after delta t is passed, then its value is increased by amount C times delta t. And how about this point? Even in this inside point, so the increase is simply given as C times delta t. And even everywhere, so increase is given as C times delta t. Of course, so please be careful. Here we have a negative sign, so please understand. It means that it is corresponding to the just uniform increase of our boundary. So let me just give you one example. When v velocity is positive, so positive value, so per second only 1 nanometer increase in its velocity or its interface. So after 10 seconds, of course, please don't be confused with this velocity itself. So this is quite slow. So I'm just showing you some any arbitrary value. So don't be fooled with this exact number. So is this really the growth of our process is corresponding to 0.1 angstrom per second? It really depends on the situation. So don't be confused. So this is just a numeric value we wanted to evaluate for simplicity. After 10 seconds, so phi will decrease, not increase, decrease 1 nanometer everywhere. Why? Because this is corresponding to 0.1, and here we have minus sign, and steps is 10 steps because we have once for 1 second minus 0.1, and if we have 10 seconds, then that will give us just 1 nanometer decrease. So please have a look at your result. This is the one after 10 seconds, and this is the one after 20 seconds. So how does it look like? These solid lines are showing the shape of your original nanosheet. After that, if you spend 10 steps, then the shape will be increased or expanding, and when you go to 20 seconds, and it becomes even wider. Of course, when you have a look at this point, yes, this is corresponding to 1 nanometer, and yes, when you have a look at this distance, then that will become 2 nanometer. It is expanding. So actually this flat or this plateau or flat part, so the shape is just changing. It's not that interesting, but please have a look at this part, this corner part. How does it look like? It just looks like a part of a circle because it is constantly increasing, and you can see that also here you have almost a semicircle because the initial starting shape was also close to the semicircle, and it is getting bigger. So what you can do is in this example is simply just to construct the initial level set function, and after that during the time evolution just to add or subtract the value. Then you will have a different value for your level set function. After that, when the process is over, just to try to reconstruct your boundaries. Then you will get this deposition simulation. Okay, so of course, if we wanted to make the real physical meaning out of this one, then we must introduce certain value corresponding to the real physical parameter. Also, time step should be taken from certain numerical consideration and also actual physical process time. For example, if you grow your certain structure with 10 minutes, then you have to set your process time as 600 seconds with reasonable normal vector velocity. Then you will get reasonable value. So that is the one we have to be careful. However, that is something like related with physics, and at least in its numerical operation, it is that so simple in this isotropic case. Then how about etching? Now think about etching. Here we have a nano sheet and we wanted to etch it away. Then if velocity is given as a negative, it means that it is shrinking, and after 10 seconds, then of course we will have 1 nanometer reduction of its thickness in one side and on other side, so we can do it quite easily. Natural question is, okay, looks like good, but it's 20 seconds and we have a very only thin layer of nanosheet, and what happens if we go to even further, like 30 seconds? So what you can expect is disappearing nanosheet. And can you get that one? Yes, you can. So if you spend more time, then your values will be increased quite a lot. However, please be careful. After a few more seconds, so your level, all of your level become positive, so you have no longer this nanosheet. But in that case, what is the level? Actually, since there is no level, no material at all, we just lose the physical meaning of that level set function. In that special case, we should be careful. Just increasing it further and further, then we can have quite a large value for our phi function, but it doesn't mean anything. So although the basic principle is that simple, but please be careful whenever we do introduce some change of shape, then we have to be careful and check whether that is corresponding to the physical situation or not. Okay, so that was the nanosheet example, and I intentionally made these two asymmetric corners. But how about other example? In the previous lecture, I just told you that determining whether a point is interior or exterior can be done by, for example, if one point is located here, then just to rotate in this counterclockwise and check whether that point is located in the left hand side or right hand side. That was my algorithm. However, I found that my algorithm was not generally valid, so please consider this example. So this is the counter example. Yes, certainly this point is now have the value at the point inside our polygon. So in this case, please try to estimate. If we say this is the direction of our movement, this is on the left side, left, yes, still left and left, good, and here still, oh, is it still left? Actually not. And now it is left. And how about this? Is this on the left or right? And this is right and left, left and left. So my previous algorithm was not valid for this kind of shape, and the point is this is concave polygon. So it's not convex. Convex means that something like this. In this case, we can say my previous algorithm works quite well. However, if we have this kind of shape, then my previous algorithm didn't work. So since we are now considering non-convex concave polygon, so we need a better algorithm to determine the interior exterior points. So I have searched the internet and find two algorithms to calculate this problem. One was just to lay crossing, or I don't remember exactly, but lay tracing or lay crossing. So in this case, now think about a certain arbitrary shape of a closed surface, and here we have an interior point and here we have exterior point. So if we have exterior point, then what will happen? If we just draw one line, then how many crossings can we get? So we can get one crossing point and another crossing point. So we have two crossing points, and let's have a look at this one. So 1, 2, and okay, so this is one lay. I'm not saying that our lay should be obtained from both sides, but please consider only one side. Then what will happen? If we have this way, how many crossing points are found? Only one single crossing point is found. So simply speaking, now think about this one. Whether you have an internal point or external point, if you go to infinitely far away from your polygon or your closed surface, eventually you will arrive at the status of exterior points. And if you start from an interior point, then you at least once you have to cross the border. Okay, and if you start from exterior point, then if you go to this way, there is no crossing point. Or if you have one exterior point, then another possibility is first enter into the inside of the polygon and once again escape. So always enter and escape, they are a pair. It is because eventually we always at the outside of our polygon. So always these actions enter into enter into the system or the boundary and escaping from it. So therefore each of entering and escaping contribute one crossing point, always we have 2 or integer multiple of 2 crossing point if we start from external point. However, if we start internal point, then at least once we have to have only escaping, not entering. So simply speaking, if you start from internal point, then you will have 2n plus 1, the odd number of crossing points, and from external points, then you will have just an even number of crossing points. So that is quite a simple way to check whether your system is your point is belonging inside or outside of a certain polygon. That was one thing, and another one was just collecting the angles. So just try to make a sum of angles, so you will get the same operation. So we have 2 different algorithms, so please try to implement any of it, so both of them will work quite well. So I have improved my implementation, and as a result, for this small hole, our level set function is now given here. Here we have blue part corresponding to what? This part is corresponding to our internal area, and outside we have positive values. And this is the file I have used to generate this structure. Here we have very shallow and narrow hole, and what will happen if we try to just deposit certain material on it? Then please have a look at it. So after 1 second, so please have, of course in this case actually this part or that part, even this substrate part is expanding, but this is none of our interest, so please concentrate on only this part. So compared with this solid line, you immediately understand, okay, now the hole is diminishing. So please have a look at this one once again. Now you can see that after 2 seconds, just 2 steps, so holes becoming quite narrow. After 3, okay, now we have a very shallow one, and after 4 we have this one. So what will happen if we proceed further and further? Then we will have still the distance between this and that cannot be completely eliminated, but anyway we will have certain shape which do not have the clear hole like this, so you can do it. So this is corresponding, if you use it properly, then this is corresponding to the deposition simulation on the hole. And also you can, by applying the negative value into it, so you can also make such kind of etching process. But in the case of etching, so also you will have etching of this part, also etching of this part. So you will have different shapes. So please have a look at your own result. So let me just quickly wrap up today's lecture. So unfortunately, today's lecture contains only a constant surface normal velocity. The details are not considered. For example, if we are considering anisotropic behavior of our surface growth, then actually we have to define different values. But right now we don't constant. So sorry about that, this typo. We have introduced a constant surface normal velocity. So, well, if we adopt this simple one, then equation becomes extremely easy to implement. So you can immediately write down your own level set code. So please try to test your program, your own examples. So in my opinion, actually your more or less your effort should be spent for developing the internal or interior and exterior point determination. So because our previous algorithm worked not properly, so please improve the routine, and after that you will get the immediate working result for this simple case. Of course, it's my pity to not to prepare more advanced topics for level set method, but please understand this is the very first semester to introduce our level set method, and I will continuously improve the lecture contents. Okay, so do you have any question? No? Okay, then I would like to wrap up today's lecture a little bit early. Okay, see you next Tuesday, and we have only 2 on-site lectures due to my busy schedule. Thank you.